Hello everyone, my name is Bhargav. Today we are going to discuss solutions of assignment 8. In this assignment 8, we are going to solve problems based on classical cryptography and quantum cryptography. Let us look at problem number 1. In the problem 1, it is mentioned that in the RSA algorithm we are using n is equal to 247 and E is 7, and we are asked to find D, and also given that factorization of capital N is 19, and it is also given that factors of N are 19 and 13. N is 247, which is 19 times 13, and it is also given that E is 7. We know that in RSA algorithm E times D must be equal to 1 modulus phi of n. Phi of 247 is phi of 19 times 13. As both are prime numbers, phi of 19 times 13 is 18 times 12, which is 216. So we need to find D such that 7 times D is equal to 1 modulus 216. We can see that 7 times 31 minus 1 is equal to 216. That implies 7 times 31 minus 216 is 1. So इसमें लिख दिया. So we clearly see that 7 times 31 is equal to 1 modulus 216. So D is 31 in this case. So correct option is option B. Look at problem number 2. In problem number 2, it is given that n is equal to 91 and E is equal to 5 in RSA algorithm, and encryption message is given as 10, and the message is given as 10, and we are asked to find encryption of the message. So it is given that n is 91 and E is 5 and M is 10. We know that encrypted message is m power E modulus n, that implies C is 10 power 5 modulus 91. We can write this as 10 square mod 91 whole square times 10 whole modulus 91. That implies 100 square is 10 square is 100, 100 modulus 91 is 9, so 9 square is 81, so 810 modulus 91, that is equal to 91 times 9 is 819. So, minus 9 mod 91, add 91 to minus 9, which gives us 82 mod 91. So, encrypted message is 82. So, correct option is option C. Look at problem number 3. It is given that there is an old woman who goes to market with a basket of eggs, and she sets the basket down and a horse accidentally steps on it, crushing all the eggs. Now the rider offers to pay her, but the thing is she does not remember how many eggs she has exactly, but she tells the rider that when she take all the eggs out 3 at a time, there were 2 left in the basket. So, say there are n eggs, then if they are taken 3 at a time, there are 2 left in the basket. That implies n mod 3 is 2. Similarly, it is given that if you took them out 5 at a time, 3 are left, and 7 at a time, then 2 are left. We see that 3, 5 and 7 are co-primes to each other. So, consider n1 as 3 and n2 as 5 and n3 as 7, and n as product of these 3 numbers, 3 times 5 times 7. Now consider n1 as product of other 2 numbers, or n divided by n1, which is 5 times 7, 35, and n2 is 7 times 3, 21, and n3 is 3 times 5, 15. And here we are trying to use Chinese remainder theorem, where we need to find n1 inverse with respect to capital N1 inverse with respect to small n1, which is same as 35 modulus 3 is 2. So, 2 inverse mod 3, which is 2, because when we multiply 2 with 2 we obtain 4, and 4 modulus 3 is 1. So, 2 inverse modulus 3 is 2. Similarly, alpha 2 is 21 inverse mod 5, which is 1 inverse mod 5, which is 1, and alpha 3 is 15 inverse mod 7, which is again 1 inverse mod 7. So, again 1. Now, using Chinese remainder theorem, required number is sigma I consider these as x1, x2, x3. Required number is xi, ni, alpha I, that is 2 times 35 times 2 plus 3 times 21 times 1 plus 2 times 15 times 1, that is equal to 140 plus 63 plus 30. We obtain this number modulus small n, which is 3 times 5 times 7 mod 105. This is 233 mod 105. 2 times 105 is 210. Subtracting 210 from 233, we obtain 23. So, correct answer is 23, option B. We note that 23 is least possible number of x. Any number which is of form 105 times n plus 23 is also a possible answer, but as we are asked to find the smallest possible solution, 23 is the correct answer. Look at question 4. Question 4 is based on BB84 protocol. We are given that sequence of bases which Alice has used and also sequence of bases which Bob has used. Let us write them down. Alice, Bob. The sequence of bases used by Alice are D, H, 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 D, D, H, D, H, and Bob D, D, H, D, H, D, D, H, H. And the code received by Bob is 1 1 0 1 1 0 0 0 1. So, the shared code contains the numbers where Alice and Bob agreed on the basis. We see that in the first bit both Alice and Bob has used same basis. So, this number is included in the shared code. Here they use different bases, so this is not included in the shared code. So, these are the bits included in the shared code. So, the shared code between Alice and Bob is 1 0 0 1. So, the correct option is option B. Let us look at problem number 5. This problem is also based on BB84 protocol. Here in the question it is given that there is presence of another entity Eve which tries to get the code which is shared by Alice and Bob. So, here we are asked to find what is the probability that presence of Eve will get undetected. Let us find the probability of Eve getting detected. To have Eve detected, Eve should use a basis different from that of Alice and Bob. Suppose Alice and Bob has used horizontal basis, then probability of Eve using another basis is half. And after that, even though Eve might have used different bases, if he had got the same bit as that of Alice and Bob, then he might not get detected. So even after using a different basis than Alice and Bob, Eve should get a different result from the result obtained by Bob. So the probability of Bob obtaining different result is half. So Eve will get detected if and only if Alice and Bob has used the same basis and Eve uses a different one, and in that case if Bob obtains a different result than Alice, then they observe that a third person is present in the communication. So we have two different events whose probabilities are half. So probability of Eve gets detected is half times half 1 by 4. So probability of Eve not getting detected is 1 times 1 by 4, which is 3 by 4. We calculate this probability for 1 bit, but it is given that they have checked over m bits. So this event has to be repeated for m events. So probability of Eve not getting detected in m instances 3 by 4 power m, because these m events are independent. In each case Eve should not get detected. So we need to multiply 3 by 4 m times, which gives us a result 3 by 4 raised to the power m. So the correct answer in this case is D. Let us look at problem number 6. In problem number 6 is based on BB84 protocol. Here we are asked to find disagreement. Disagreement is already defined in the problem, which is probability of Alice preparing bit 0 in basis B, but Bob measures 1, plus probability of Alice prepares 1 in basis B and Bob measures 0. Here there is attack launched by Eve, where Eve uses a different basis. Let us calculate the disagreement AB. Here we see that is 3 by 4 and is 1 by 4. Let us calculate all these things. So when do we have a disagreement? If Alice sent 0 but Bob obtains 1. In this case Eve might get 0 or 1. In other cases Alice sends 1 but Bob receives 0, and Eve may get 0 or 1. These are the 4 cases where there is a disagreement. So, probability of these events and probability of choosing one of the bases is half by Eve. So, the disagreement is equal to half times probability of sum of probability of these things. So, what is the probability of this? Probability of obtaining 0 by Eve when 0 is sent by Alice is say Eve has used alpha minus. So, when the 0 is sent by Alice, obtaining a 0 is of probability 1 by 4, and after Eve measures 0, the probability of obtaining 1 by Bob is 3 by 4. So, probability of having 0 0 1 is 1 by 4 times 3 by 4. Consider any other case. Suppose Alice sends 1 and Eve measures 0. Probability of this happening is, suppose Eve has used alpha plus basis. Measuring a 0 in alpha plus basis when 1 is sent is 3 by 4, and Bob measures 0 is 1 by 4. In every case we have probability 3 by 4 times 1 by 4. So, it is 1 by 4 times 3 by 4, which is half times 4 times 1 by 4 times 3 by 4, which is equal to 3 by 8. So, the correct answer is option D. Let us look at problem number 7. Problem number 7 is same as that of problem number 6, but the bases used by Alice and Bob are changed to plus and minus. We know that plus is nothing but 0 plus 1 divided by square root 2, and minus is 0 minus 1 by square root 2. So, 0 is plus times 0 is plus minus divided by square root 2, and 1 is plus minus by square root 2. So, rewrite the basis used by Eve in terms of plus and minus. It is given that alpha plus is root 3 by 2 times qubit 0 and 1 by 2 times qubit 1, which is root 3 by 2 times plus root 2 plus half times plus minus by root 2, which is root 3 divided by 2 root 2 times plus minus plus 1 by 2 root 2 times plus minus qubit minus. So, alpha plus is root 3 plus 1 divided by 2 root 2 times plus plus root 3 minus 1 by 2 root 2 minus. Similarly, we can calculate alpha minus. Alpha minus is minus half times 0 plus root 3 times 1, which is nothing but half times plus root 3 by 2 times minus by root 2. We obtain root 3 minus 1 by 2 root 2 plus minus 1 minus root 3 minus 1 minus root 3 by 2 root 2 times minus. And we calculate square is root 3 plus 1 by 2 root 2 whole square minus alpha plus is root 3 minus 1 by 2 root 2 whole square, and plus alpha minus is root 3 minus 1 by 2 root 2 whole square, and minus alpha minus square is minus 1 minus root 3 by 2 root 2 whole square. Similar to the previous solution, we have half times probability of having Alice sending a 0, but Bob receiving a 1, with Eve receiving 0 or Eve having 1. Similarly, other cases 1 0 1 0 and 1. Probability of Eve obtaining a 0 here as Alice and Bob are using plus and minus basis, 0 say 0 corresponds to a minus and 1 corresponds to a plus. So, when Alice sends a minus and Eve obtaining a minus, say alpha minus is the basis used. The probability of obtaining a negative by Eve is minus 1 minus root 3 by 2 root 2 square, and after using alpha minus basis by Eve, the probability of obtaining 1, that is plus, by Bob is root 3 minus 1 by 2 root 2 whole square. This is the same term which gets repeated 4 times. So, this term equals to half times 4 times this thing, which is equal to 2 times 1 by 8 square, taking out 2 root 2 and 2 root 2 outside, we obtain 1 by 8 whole square. 4 by 2 is 2 times root 3 minus 1 times root 3 plus 1 is 2, which is 1 by 8. So, the correct answer is option A. Let us look at problem number 8. Problem number 8 is based on B92 protocol. The question is, which of the qubits are to be kept for error checking and key generation. We know that only those qubits where Bob's outcome is either negative or 1 are to be kept for error checking and key generation. So, writing the bit qubits obtained by Bob negative plus 0 0 1 plus minus plus 0 minus 1 0, give numbering 1 2 3 4 5 6 7 8 9 10 11 12. We obtain minus here and 1 here and a minus and a 1 and a minus here. So, we need to keep first bit, 5th bit, 7th bit, 10th bit and 11th bit for error checking. So, the correct option is option A. Let us look at problem number 9. Problem 9 is based on B92 protocol. Here we are asked to find key that is being distributed in this specific run. Bob's states after error checking are given as minus 1 1 minus minus 1 minus 1 minus and minus. We know that Bob's outcome minus corresponds to Alice input state 0, which has a bit value 0, and similarly 1 has correspondence with Alice input state plus, which corresponds to bit 1. So, qubit minus corresponds to qubit 0 and qubit 1 corresponds to bit 1. Similarly, for every other qubit, if we write the encoded value, it is 1 0 0 1 0 1 0 0, which is same as option C. So, the correct answer is option C. Problem 10. Which of the following algorithms can be used to break RSA crypto system? We know that RSA crypto system is based on observation that a large number is difficult to factorize, but we have a quantum algorithm which can factorize any large number in short span, which is Shor's algorithm. So, we can use quantum Shor's algorithm to break RSA crypto system. So, if you are given any n, we can divide into factors. So, we can compute phi of n. Based on phi of n, we can compute d. So, we can decrypt any message encrypted using RSA. So, the correct answer is quantum Shor's algorithm, which is option C. Let us look at multiple correct type answers. It is given that in RSA algorithm, capital N is 851 and the factors are 37 and 23, and we are asked to find which of the following are acceptable encryption exponents. We know that E times D must be 1 modulus phi of n, and phi of n is 36 times 22. This implies ED minus k times phi of n should be 1. This implies that there exists some k such that ED times k times phi of n is 1, and we see that E times D minus k times 36 times 22 is equal to 1. Suppose E and D has a common factor which is greater than 1, then it divides whole term on left hand side, but cannot divide the number on right hand side. So, E cannot have a common factor with 36 times 22. So, GCD of E comma 36 times 22 should be equal to 1. So, in the given options 5, 7, 9, 11, 5 does not have a common factor with 36 times 22. So, 5 can be a possible E, same with 7, but 9 can divide 36. So, we cannot use 9, and 11 can divide 22. So, we cannot use 11. So, the correct options are option A and option B. Let us look at the last question. We are asked to find value of phi for different numbers. Phi of 21 is phi of 3 times 7, which is 2 times 6, that is 12, which is not equal to 14. So, option A is incorrect. Phi of 13, as 13 is a prime number, phi of 13 is 13 minus 1, 12. Phi of 21, we have already calculated it to be 12, which is not equal to 20. So, option C is incorrect. Phi of 35 is phi of 5 times 7, which is 4 times 6, that is 24. So, option B and D are correct. So, in this last assignment we have dealt with problems based on classical cryptography and quantum cryptography. In this 8-week course we have dealt with many concepts of quantum information and computing, and here we are closing this course with quantum cryptography. Hope you like this course. Thanks.